Hello. In this video, I'm going to try to answer the question, why do we have to rationalize the denominator? What's the point? So, to explain what I mean, look at this expression here, 1 over the square root of 2. Now, if you've learned about radical expressions like this, you may, depending on who you had for a teacher or what book you were using to learn from, you may have learned that there's something wrong with an expression like this that has a square root of something in the denominator. Like I said, depending on who you learned this from, you might have learned that this is a really bad way of writing a number with a square root in the denominator. That there's something wrong or indecent about that, and that leaving an answer like this, it's kind of like leaving your house without pants on. It's something that you don't want to do. And if you had a more mellow teacher, you might have learned, well, there's nothing inherently wrong with having a square root in the denominator, but you still want to know how to transform something like that into a different form that doesn't have a square root in the denominator. So in this case, you would accomplish that by multiplying the original fractional expression, 1 over the square root of 2, by the square root of 2 over the square root of 2, and that turns it into the square root of 2 over 2 itself. So doing that, taking something like 1 over the square root of 2 that has a radical expression in its denominator and rewriting it so that it doesn't have a radical in the denominator is called rationalizing the denominator. Now, in this video, I'm not going to explain how to do this. Maybe you already know. If you don't, there's places you can learn. I do have one of my old videos where I do explain how to rationalize the denominator and show some examples of doing that. So I'll link to that in the video description. But the point of this video is to talk about why you would want to rationalize the denominator. Why is it any better to write a number as the square root of 2 over 2 rather than as 1 over the square root of 2? Well, sometimes rationalizing the denominator of a number that's written with a square root in the denominator really does make the result look simpler. For example, the number 12 over the square root of 3, if you rationalize the denominator, it becomes 4 times the square root of 3. And that does look simpler. The square root of 11 over the square root of 10 can be simplified to the square root of 110 over 10 itself. So instead of having 2 different square roots, 2 different irrational numbers involved there, it just has 1. Or the expression 1 over 2 plus the square root of 3 is equal to just 2 minus the square root of 3. No more fractional expression, just 2 minus the square root of 3. It's the same number, but written in a simpler form. And I'm not going to explain how you get from one to another, but at least some of these examples are taken from that other older video that I was talking about. So if you can't figure out for yourself how I get from one to the other, you can look at that old video. So like I said, sometimes rationalizing the denominator really does make the result look simpler, but sometimes it doesn't. I mean, why is it any better? Why does it look any simpler to write the square root of 2 over 2 instead of 1 over the square root of 2? They both have the square root of 2 in them. Why is it any better to have that on top instead of on the bottom? Or take 2 over the square root of 3. There, if you rationalize the denominator, you simplify it to 2 times the square root of 3 over 3. But does that really look any simpler? It's still got a square root of 3, it's still got a 2, but it's also got a separate 3 hanging around there. So in a way, that looks more complicated. Why is that any better? So let me start by pointing out that in math, there are many situations where the same thing, the same number or the same expression can be written in more than one way. So you might have things that look different, but are actually equivalent. So the kind of radical expressions we were just looking at, those are one example of this, but there are plenty of other examples. For example, 5/4 or 1 1/4 or 1.25 all refer to the exact same number. They're just different ways of writing that same number, either as an improper fraction or a mixed number or a decimal. The expression 2 times the quantity x plus 10 is equivalent to the expression 2x plus 20, because multiplication distributes over addition. So either one of those is equivalent to the other. They mean the same thing, they have the exact same value, they're just different ways of writing the same expression. Or take the linear equation 4x minus 3y equals 15. That's equivalent to the equation y equals 4/3 x minus 5. You could take the equation on top, and by doing some legal algebraic manipulations to solve it for y, put it into the form of the equation on the bottom there. In a way, they're the same equation. They have all the same solutions. They represent the same straight line if you graph the equation. They're just different forms for that equation, but they are equivalent. So they're just different ways of writing what's essentially the same thing. And when there are different ways of writing the same thing, it's usually important to be able to tell when two things that look different and are written in different ways really are equivalent to one another, or to be able to transform an expression from one form into another. So yet another example of that would be when you're working with fractions, something like 2/4 is equivalent to 3/6, which is equivalent to 17/34, which is equivalent to 50/100, which is equivalent to 1/2. So these are all different ways of writing the same number. They all represent the exact same number, just written in different ways. Which way is best? Well, that might depend on the context, on what you're doing. If you were going to take this number and add it to another number that was in the form of a fraction with a denominator of 34, you would probably prefer your number to be in the form 17/34, because in order to add fractions, you need them to have a common denominator. If you were thinking in terms of percentages, you might like your number to be written as 50/100, because then you can right away see, oh, that means 50%. But for most cases, probably the best or simplest way of writing this particular number is to write it as 1/2, 1/2. That way it's in lowest terms or simplest form. So in cases where the same thing can be written in more than one way, there are different forms of the same number or same expression, often one particular form is considered to be the simplest or the standard form. So with fractions, the simplest form would be one where your numerator and your denominator don't have any common factors. Because if they did have a common factor, you could divide out that common factor and reduce the fraction to lowest terms. So often there's a simplest form, and there are rules for taking a number or an expression and writing it in simplest form. And often that simplest form or standard form is unique. There might be many different ways of writing the same expression, but only one way of writing it in that standard or simplest form. So if you wrote it in one way and somebody else wrote it a different way, and then you both simplified down to that standard form, your answers should look identical in that standard form if they really do represent the same thing. So for radical expressions, that is, expressions that involve the square root or some other kind of root, like a cube root of something, one of the conditions for being in simplest form is that there should be no radicals, that is, no square roots or any other kind of roots in the denominator of the expression. And also no fractions under a radical sign, like the square root of 1/2. Okay, so why? Why is that one of the conditions for being in simplest form? Why is it simpler for a radical expression not to have radicals in the denominator? Well, as far as I know, there's no official answer to this. It's not like all the mathematicians of the world got together in a council and decided this. But here's what I think are some reasons that make sense. Here's why I think is the rationale behind this rule or condition. First of all, as we've seen in some of those examples I was showing you earlier, sometimes rationalizing the denominator really does make the expression look obviously simpler. Not always, but often it does. Second, as a general rule in math, when you're doing mathematical manipulations, it's nice to have your denominators as simple as possible. It's better to have a simple denominator than to have a simple numerator but an ugly, complicated denominator. Like, for example, if you're going to be adding fractional expressions together, you need them to have a common denominator, and it's usually easier to figure out how to get that if those denominators are as simple as possible. So that's a reason I could give for why you want to rationalize the denominator, to make the denominator as simple as possible. And there are some situations in areas of advanced math where the standard form for a particular kind of number looks like something plus something times the square root of something. You got one part that's just like a number by itself, and then another part that's a number times the square root of another number. And an example of that you may be familiar with, that you may have studied, is complex numbers. The standard form for a complex number is a plus bi, where the a and the b stand for real numbers, and the I stands for the square root of -1. So there are different ways of writing the same complex number, different forms it could be in, but only one standard form. Only one way of writing some particular complex number in that standard form. And one more reason that doesn't really matter all that much today, now that pretty much everybody has access to calculators and computers and calculator apps on their phones and that sort of thing, but which probably was important back in the old days, has to do with calculation. What if you had to calculate and evaluate a number that involved a square root so that you could get a decimal approximation for that number? Which is easier to calculate by hand without a calculator? Square root of 2 over 2 or 1 over the square root of 2? So mentally take yourself back to the good old days before calculators and computers and things like that. Now, if you needed to know what the square root of 2 is, you could look that up on a table of square roots. So it's approximately 1.4142. That's the square root of 2, accurate to 4 digits after the decimal point. And if you didn't happen to have a table of square roots handy, there are ways of evaluating square roots by hand. And then if we take that square root of 2, that 1.4142, and divide it by 2, and remember we don't have a calculator, but if you've learned how to divide numbers by hand using long division, that's not a particularly difficult thing to do. Like you'd start by saying, well, 2 doesn't go into 1, but 2 would go into 14 7 times. And if you multiply 7 times 2, you do get 14. And when you subtract, you get 0, then bring down the 1. 2 goes into 1 0 times. So we need to bring down the next digit. And now 2 goes into 14 7 times. And then multiply 7 times 2 and get 14. And subtract. Bring down the next digit, the 2. 2 goes into 2 1 time. And so we've got the value of the square root of 2 divided by 2, accurate to 4 digits after the decimal point. So it's approximately 0.7071. Now, if we'd had a calculator, we could have just easily punched into the calculator either the square root of 2 over 2 or 1 divided by the square root of 2. And it would have given us that answer to as many decimal places as it had room to show us. But if we didn't have a calculator, there it was fairly easy to get a decimal approximation by hand. But if we had not rationalized the denominator, if we had left it in the form 1 over the square root of 2, to evaluate that and get a decimal approximation, we would have to take the number 1 and divide it by the number 1.4142. And that's a lot harder to do by hand, by long division. I mean, first of all, 14142 goes into 1000000 times, but then you have to figure out how many times it goes into 100000, and that's not obvious. It does turn out to be 7, and then you'd have to multiply 7 times 14142, put it down there, subtract, then keep on going to get more digits after the decimal point, and it would get really messy and complicated. It's not nearly as easy to do as dividing 1.4142 by a nice simple whole number like 2. The difference is even more dramatic if you look at this example. Remember, if you take the expression the square root of 11 divided by the square root of 10 and rationalize the denominator, you can write it as the square root of 110 divided by just the number 10. Now, if you had a calculator, either one of these would be fairly easy to punch into the calculator and get a decimal approximation. But if you did not have a calculator and you had to do all the calculations by hand, well, we could look up what the square root of 110 is. Turns out it's approximately 10.4881. And then we would just have to divide that number by 10. And it's real easy to divide a number by 10. You just shift the decimal point over one place to the right, or to the left, sorry. So that would be 1.04881. So the approximate decimal value of this number is 1.04881. Now, if we had left it as the square root of 11 over the square root of 10, we can look up that the square root of 11 is about 3.3166, and the square root of 10 is about 3.1623. But then to divide that by hand, oh, that gets really messy. You have to figure out how many times this goes into this, and multiply and subtract, and go through all the process of long division with these big ugly numbers, and that's not anywhere near as easy as this was. So anyway, that was my attempt to explain why it might be useful to be able to rationalize the denominator of a radical expression. Why that rationalized denominator version really is simpler or better, at least in some cases. Now, depending on what you're going to do with a number, it might not make sense to rationalize the denominator. It might be perfectly okay to leave it with a square root in the denominator. That's up to you or to your teacher or boss or whoever is asking you to to work the problem that has an answer like that. But as far as I'm concerned, there's nothing inherently wrong with having radicals in the denominator of an expression, but it is important to be able to simplify something like that and write it so that you have rationalized the denominator. And I don't claim to be an expert in this. There may be issues that I'm not aware of or haven't thought about. There may be other reasons that I didn't think of why you might need to rationalize the denominator of an expression. If you know of them, you're welcome to leave a comment. But this was my attempt to give you some idea in case you've learned about rationalizing the denominator and you were wondering what's the point. This is my attempt at explaining why. So, thanks for watching. I hope you found this helpful or interesting.